Good morning, everyone. I am Nicola Caterino from University of Naples PARTHENOPE, and this article, this work was made with, in collaboration with Professor Georgakis of the Technical University of Denmark, the TU, and Professor Occhuzio of my university, Smart Structural Control for Wind Turbines. As you know, wind power capacity worldwide has increased very much in the last years. And also the height of wind turbines has been grown very, very quickly from 70 meters in average in the 80s up to 125 meters in 2010. And this kind of a trend is going on up to design even higher wind turbines. So these higher turbines allow to produce higher energy, of course. On the other side, more challenging structural issues emerge, of course. These kind of structures are typically protected by automatic supervisor, safety supervisor, that, for example, make the automatic shutdown of the tower of the turbine the moment in which the wind velocity overcomes a given limit, let's say 25 meters per second. This is the typical value. Of course, the shutdown is a strongly undesired action for economical and social issues. Then there is another need to reduce the size of the cross-section of the tower. Because higher tower, higher solicitation, then higher cross-section, and higher costs and higher difficulties to move the pieces useful to build these huge structures. So the idea we presented here is a smart structural control of a wind turbine that is based on the basic idea of changing the constraint at the base. So passing from a idealized, fixed base support to a variable restraint that is more flexible and that is above all variable and can be driven by a semi-active controller over the time, over the excitation by the wind. So the wind. So the supported base is an hinge, then coupled with the two elastic springs and two dashpots that are two semi-active dampers. Semi-active dampers that are magnetorological dampers in this case. This idea has been implemented at the DTU laboratory in Copenhagen with reference to this 100 meters tall commercial wind turbine. The model is 1/20 scaled, and the dampers that we used are prototypes from Maurer-Sohn, a German company, and this is a quick sketch of the behavior of such device that probably you already know. These are different force displacement cycles of response of the same damper once the damper is fed by different current from 0 amperes up to 2.7 amperes, and the current intensity changes the magnetic field within the dampers, so changes the mechanical behavior of the fluid that is within the dampers, and changing the reacting force from, in this case, these are experimental tests of the dampers that we use for the wind turbine, from 2 or 3 kilonewtons up to about 30 kilonewtons of response force. And this is the sketch of the experimental setup. So the moving is imposed at the base with the shaking table facility. And this is the hinge, central hinge. These are the two dampers, magnetological dampers, and these are the two springs, and this is the tower that is 5 meters long. And the mass at the top stands for simulating the presence of the nacelle and of the blades. This is a zoom of the same picture. We can see the presence of the load cell to measure the force within the damper, the lasers in order to measure displacements. We cannot see, but there are here some strain gauges in order to measure the deformation and then derive the stress at the base of the tower. These are some pictures from the laboratory where you can see the pieces were installed. This is the tower, and this is the electronic equipments used to acquire signals and to control the damper. But I think it is the case to skip on. The control algorithm. We build a special control algorithm for such kind of application that is based on the full state feedback theory, and relying on the final objective of a favor rigid displacement of the tower, like this, and to reduce the elastic displacement, so to reduce the bending moment at the base of the tower. In this case, of course, you pay the cost of increased displacement at the top. So with this algorithm, we aimed at reducing this undesired effect. So this algorithm is based on the state of the system and gain matrix, that is this one. And this is the desired control force, the force that should be applied if we have an active damper, not a semi-active damper. So the actual MR control force is controlled by these simple expressions, aiming at mimicking as much as possible the desired control force. So when the desired control force and the actual control force have a different sign, the only things that we can do is to switch off the damper. In the other case, we decide to switch on or switch on the dampers, increasing or decreasing the current in dependence on the fact that we are close or less close to what we desire the damper behaves. Two different kinds of wind loads, two very different kinds of wind load have been considered in these experimental activities: an extreme operating gas and a parking load. The first one is a sharp increase. The first one is this. So a short-term acceleration at the base with a few peaks, but large peaks. So a sharp increase, then decrease in wind speed in a short period of time. The other one is a buffeting that can occur when the turbine is parked for shutdown, for example. So they are very different for duration, 2 minutes, 10 seconds, and for frequency contents. These acceleration time history have been imposed at the base and have been derived by Professor Chen and Georgakis from DTU, using a software that they built. And the software is able to convert the effect of wind loads in terms of equivalent base acceleration time histories. So in this case, this way, we were able to make this kind of shaking table movement to simulate not seismic action, as we are more. It is more common for us, but to simulate something that is related to wind action. These are some results related to the first action, the extreme operating gas. And we can see here the maximum base stress at the base of the tower over the time, and this is not written, but this is the top displacement. And with the gray line is the fixed base tower. So we removed the dampers and installed the very rigid rods in order to obtain the fixed base condition. And the black line is the semi-active controlled response. And the reduction in terms of stress is so evident. The reduction is even minus 70% more or less. So a huge reduction, we can say. But we pay, as I anticipated, we pay the cost of increasing the peak displacement of 28%. The commitment of the client, in this case the D2, is to do not enlarge the top displacement over the 30%, because they consider that 30% is acceptable, and the second order effects associated to this kind of horizontal top displacements are acceptable, still acceptable. For the other kind of accelerogram, so wind load PRK parking, we show a very small time window in the more strong part of the load, and in this case we can see that the reduction in stress is more or less 50%, and that the displacement, the top displacement, remains more or less the same that we recorded during the fixed base experiment. So this is an interesting result, and in this case I want to show again the shape of the accelerogram at the base. In this second case, it is so different. It is less impulsive. So the damping capabilities of the magnetological devices is more able to emerge in this case. In the case of impulsive loads, it is less clear, but the effects in terms of making more flexible the base restraint is even evident also in the first case. So I'm going to conclude. The semi-active strategy based on a variable restraint at the base has been presented here, and we showed the first experiments that, as far we are concerned, have been made with reference to a wind turbine semi-active controlled, and results we think that are encouraging to investigate more and more about this kind of strategy. Also designing other kind of control algorithms, for example, or investigating the effect of different kinds of wind loads. Thank you. I'm closing.
How did you calculate the aerodynamic loads on the turbine itself?
Sorry?
How did you calculate the aerodynamic loads on the turbine?
I did not calculate. I used the one that in a previous work, Professor Chen and Yongagis, that you can read the reference on the paper, derived with reference to these two kind of wind loads in a previous work. So I took from them the accelerograms, just this. Okay, so I'm not expert at wind engineering. This is my first application. But so I asked them, because this work was made in collaboration, to give me the acceleration.
So you basically applied an acceleration on the mass that's on top?
At the base.
At the base?
At the base, yes, with the shaking table.
Okay,
yes, because this kind of base acceleration equivalent is derived with that software from D2, just measuring what is the time history acceleration that makes similar effects to the ones that you derived with the actual wind load.
I could be wrong. The problem is coupled. Like, once the wind comes on the turbine and the base starts moving, then the base starts affecting the motion of the turbine itself starts affecting the flow on it.
Yes.
And it, okay, just, I bet I could be.
Yes, this kind of equivalence, wind load with the base acceleration is very strong, a strong assumption. But it is you have to think that it's the first application of this kind of, worldwide, because it is not so easy to test some kind of application at example for example in a wind tunnel. So in some way you have to do. So we are encouraged to investigate more, but we know that this is not the last point.